800 million users on a single PostgreSQL primary, and OpenAI made it work without sharding.
Wait, they're running ChatGPT on one database? How is that even possible? So we're breaking down their query optimizations, the single primary architecture, and how they handle failover.
By minute 4, you'll know their exact playbook for scaling past every limit. Let's get into it.
Welcome to the AI Daily Podcast. Today's news and a deep dive to help you stay ahead in AI.
Today, we're diving into scaling PostgreSQL to power 800 million ChatGPT users.
Stick around to the end for this week's headlines. Let's dive right in.
So let's talk about one of the most remarkable scaling stories in tech history. How OpenAI took PostgreSQL, a database that's been around since the 1980s, and scaled it to handle 800 million ChatGPT users. That's not just impressive, that's borderline insane when you think about what each of those users represents in terms of database operations.
Right, and what strikes me is the choice of PostgreSQL itself. When you're building something that could potentially serve hundreds of millions of users, wouldn't your first instinct be to reach for something like DynamoDB or Cassandra, something designed from the ground up for massive scale?
That's exactly what makes the story so fascinating. OpenAI didn't just scale a database, they scaled a traditional relational database to handle workloads that would make most DBAs break out in a cold sweat. We're talking about a system that went from 0 to 100 million users in just 2 months. That's faster growth than TikTok, faster than Instagram, faster than anything we've seen before.
And each ChatGPT conversation isn't just a simple read operation either. Every message generates multiple database transactions, storing the conversation history, updating user state, managing context windows, handling token counts.
Exactly. Let me put this in perspective. When a user types a message to ChatGPT, the system needs to retrieve their entire conversation history, maintain the context, generate a response, store that response, update usage metrics, and do all of this while maintaining sub-second response times. Now, multiply that by 800 million users, many of whom are having multiple conversations simultaneously.
So why PostgreSQL? I love Postgres as much as the next engineer, but this seems like pushing it way beyond its design parameters.
There are several reasons, and they're quite instructive for anyone thinking about database choices at scale. First, PostgreSQL's maturity. We're talking about a database with over 35 years of battle testing. The edge cases have been found, the bugs have been squashed, and the behavior is predictable. When you're serving 800 million users, predictability is worth its weight in gold.
But surely the licensing played a role too.
Absolutely. PostgreSQL's permissive open source license means OpenAI could modify it, extend it, and optimize it for their specific use case without worrying about licensing fees that would scale with their user base. Imagine paying per-user database licenses for 800 million users. That's a CFO's nightmare.
And there's the ecosystem factor too, right? The tooling, the expertise available in the market?
That's a huge point. PostgreSQL has one of the most vibrant ecosystems in the database world. Extensions like pgvector for vector similarity search, which is crucial for AI applications. Tools like pgbouncer for connection pooling, which becomes critical at this scale. And perhaps most importantly, you can actually hire PostgreSQL experts. Try finding engineers with deep expertise in some proprietary database system. It's much harder and much more expensive.
Coming up, we'll dig into exactly how they pulled this off, the specific architectural decisions, the optimizations they had to make, and what broke along the way. Because I'm betting not everything went smoothly when you're pushing a database this hard.
Let's dive into the technical architecture of how you actually scale PostgreSQL to this level. The first thing to understand is that this isn't one PostgreSQL instance. That would be impossible. We're talking about a sophisticated sharding strategy that distributes the load across multiple database clusters.
How do you even begin to shard something like ChatGPT? User conversations are inherently stateful. You need the entire conversation history to maintain context.
OpenAI likely uses a combination of horizontal and vertical sharding strategies. The most obvious sharding key would be user ID. Each user's conversations stay together on the same shard. This maintains data locality and reduces cross-shard queries. But here's where it gets interesting. They probably also have separate clusters for different data types. Hot data, like active conversations, might live on high-performance NVMe storage, while cold data, like conversations from months ago, could be on cheaper, slower storage.
But even with sharding, each individual shard is still handling massive load. What kind of optimizations are we talking about at the PostgreSQL level?
This is where it gets really interesting. First, connection pooling becomes absolutely critical. Each PostgreSQL connection consumes memory, typically 5 to 10 megabytes. Without connection pooling, 10,000 concurrent users would need 50 to 100 gigabytes of RAM just for connections. Tools like PG Bouncer or PG Pool 2 become essential, maintaining a small pool of actual database connections while multiplexing thousands of application connections.
And I'm guessing they've had to get creative with caching strategies.
Absolutely. You've got multiple layers of caching here. At the application level, they're likely caching user session data, recent conversation contexts, and frequently accessed metadata. At the database level, PostgreSQL's shared buffers would be tuned to keep hot data in memory. They might be running with shared buffers set to 25 to 40% of system RAM, way higher than the default.
What about write performance? Every message generates multiple writes: the user message, the AI response, token counts, timestamps.
This is where PostgreSQL's write-ahead logging architecture actually becomes an advantage. Writes go to the wall first, which is sequential I/O, much faster than random I/O. They're probably running with synchronous commit set to off for non-critical data, trading a small amount of durability for massive performance gains. For critical data, they might use synchronous replication to standby servers.
Speaking of replication, how do you handle read scaling with that many users?
Read replicas and lots of them. PostgreSQL's streaming replication is rock solid, and you can have dozens of read replicas per primary. The challenge is managing replication lag. When you're pushing this much write traffic, replicas can fall behind. OpenAI probably uses a combination of synchronous replicas for critical reads that need consistency and asynchronous replicas for analytics and reporting workloads that can tolerate some lag.
The monitoring and observability challenges must be insane at this scale.
You're absolutely right. When you're running hundreds of PostgreSQL instances, traditional monitoring approaches break down. They're likely using tools like Prometheus with custom exporters, tracking metrics like transaction rates, lock weights, cache hit ratios, and replication lag across all shards. But here's the thing. At this scale, you can't react to problems manually. They must have extensive automation for things like failovers, rebalancing hot shards, and scaling up replicas during traffic spikes.
What about the operational challenges, upgrades, maintenance, schema changes?
This is where the pain really comes in. PostgreSQL upgrades typically require downtime, which is unacceptable when you're serving 800 million users. They're probably using techniques like logical replication to perform zero downtime upgrades, spin up new clusters running the new version, replicate data over, then cut over traffic. For schema changes, tools like PT Online Schema Change or the built-in concurrent index creation become essential.
And let's talk about the hardware side. What kind of infrastructure are we looking at?
Based on typical PostgreSQL deployments at scale, each shard is probably running on instances with at least 64 to 128 CPU cores and 256 to 512 gigabytes of RAM. Storage would be enterprise NVMe SSDs with ridiculous IOPS. We're talking 100,000 plus IOPS per instance. Network bandwidth becomes crucial too. With streaming replication and client traffic, you need 10 gigabits plus network interfaces. And all of this is replicated across multiple availability zones for fault tolerance.
Stick around. We'll give you the exact checklist of what you need to consider if you're planning to scale PostgreSQL for your own AI applications, plus what OpenAI's approach teaches us about the future of database architecture.
So let's talk about what platform engineers can actually learn from OpenAI's PostgreSQL scaling journey. The first big takeaway is that boring technology can be incredibly powerful when pushed to its limits. PostgreSQL isn't sexy, it isn't new, but it's battle-tested and well understood.
Right, and for teams considering their database strategy for AI workloads, what's the decision framework here?
Start with your actual requirements, not hypothetical scale. OpenAI didn't start by planning for 800 million users. They started with PostgreSQL because it was a solid choice for their initial needs. The key is choosing technology that can grow with you. PostgreSQL's extensibility meant they could add vector search capabilities, optimize for their specific query patterns, and scale horizontally when needed.
What about the build versus buy decision? There are managed PostgreSQL services that promise to handle scaling for you.
That's a critical consideration. For most companies, managed services like Amazon RDS, Google Cloud SQL, or Azure Database for PostgreSQL are the right choice up to a certain scale. But when you're pushing the boundaries like OpenAI, you need more control. They're likely running their own PostgreSQL deployments on raw compute instances, giving them the ability to tune every parameter, modify the source code if needed, and optimize for their specific workload.
So what's the checklist for teams thinking about scaling PostgreSQL for AI workloads?
First, nail your sharding strategy early. Resharding data is painful and risky at scale. Choose a shard key that distributes load evenly and minimizes cross-shard queries. For AI applications, user ID or tenant ID usually works well. Second, invest in connection pooling from day one. PG Bouncer is the standard, but evaluate your specific needs. Third, plan for read scaling with replicas, but understand the consistency trade-offs. Your application needs to handle the fact that replicas might be slightly behind the primary.
What about specific PostgreSQL configurations for AI workloads?
For AI applications, you'll want to tune several key parameters. Set shared buffers to 25 to 40% of RAM instead of the conservative default. Increase work mem for complex queries. AI applications often do large sorts and aggregations. For write-heavy workloads, tune checkpoint segments and checkpoint completion target to smooth out I/O spikes. And critically, if you're using PG vector for embeddings, make sure you're using the right index types. HNSW indexes for approximate nearest neighbor searches can be orders of magnitude faster than exact searches.
What are the warning signs that you're hitting PostgreSQL's limits?
Watch for connection pool exhaustion. If you're constantly hitting max connections, you need better pooling or more shards. Monitor replication lag religiously. If replicas can't keep up, you need faster storage or more aggressive partitioning. Lock contention is another killer. If you see processes waiting on locks, you might need to redesign your schema or queries. And perhaps most importantly, if your backup and recovery times are exceeding your RTO/RPO requirements, you need to rethink your architecture.
Looking ahead, what does this mean for the future of databases in AI applications?
We're seeing a convergence of traditional relational databases and specialized AI data stores. PostgreSQL adding vector capabilities, traditional databases adding JSON and time series. The lines are blurring. The lesson from OpenAI is that you don't always need specialized databases for specialized workloads. Sometimes a well-tuned, well-understood general-purpose database can outperform a specialized solution, especially when you factor in operational complexity.
And there's the open source angle too. OpenAI's success with PostgreSQL is validation for the open source model at massive scale.
Absolutely. When you're operating at this scale, being able to inspect the source code, fix bugs yourself, and optimize for your specific use case becomes invaluable. You can't do that with proprietary databases. Plus, the community effect. Thousands of engineers worldwide contributing improvements, extensions, and tools. That's powerful leverage.
So, final thoughts for our listeners who are building AI applications.
Don't overthink your initial database choice. PostgreSQL is an excellent starting point for most AI applications. Focus on getting your sharding strategy right early, invest in good monitoring and automation, and be prepared to get deep into database internals as you scale. And remember, OpenAI's 800 million users didn't happen overnight. They had time to learn, optimize, and scale incrementally. Your job is to choose technology that gives you that runway to grow. Before we wrap up, let's catch up on this week's infrastructure news. There's a fascinating new development in how we make AI models smarter at runtime. Sebastian Raschke just published a comprehensive overview of inference-time scaling techniques, and it's really illuminating how these approaches are evolving.
Inference-time scaling, that's about making models think harder when they're actually answering questions, right? Not just training them better?
Exactly. Raschke categorizes different approaches, including some really innovative recursive language models. What's striking is how these techniques can dramatically improve reasoning capabilities without retraining the entire model.
Speaking of practical AI deployment, Amazon just announced you can now build Bedrock AI agents using cloud formation templates. This is huge for enterprise teams.
The AWS blog post highlights how Agent Core simplifies what's been a major pain point, manually configuring agent infrastructure across different environments. Now you can define your entire agent setup as code.
That's going to make it so much easier for teams to standardize their AI deployments. No more clicking through console interfaces for each environment.
Now, here's some interesting industry movement. TechCrunch is reporting that Sam Altman is planning a visit to India in February, coinciding with a major AI summit in New Delhi.
India is becoming such a crucial market for AI companies. With their massive developer talent pool and growing enterprise adoption, it makes sense that OpenAI's CEO would prioritize this visit.
And speaking of OpenAI's priorities, another TechCrunch piece reveals they're making a serious push into enterprise markets this year. They've appointed Barrett Zoff to lead these efforts.
Interesting timing, considering reports of their declining market share in some segments. Sounds like they're feeling the pressure from competitors and need those enterprise contracts.
The enterprise focus makes sense. That's where the sustainable revenue is, especially as more companies integrate AI into their core operations.
That wraps up this week's news.
That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
Until next time.